This video is about solving trigonometric equations, but before we get into that, there's just one thing I'd like to have a look at, and that's one aspect of the transformation of trigonometric functions, in particular dilation. Let's start with the plot of sine x, y equals sine x, if you like, and when we plot that, here it is in blue. Okay, we're plotting it over the interval, over the domain 0 to 2 pi. All right, we see that there's a period of 2 pi. All right. If we wanted to solve the equation sine x equals 0.5, well, here's the horizontal line, 0.5. We want to set sine x equal to 0.5. We said it has two solutions over 2 pi, okay, and that is one here and one here. Two values of x that solve this equation sine x equals 0.5. If we then plot sine of 2x over the same interval, what we find here is that it has a period of pi. Okay, remember one of the transformation properties, that given a sine or cos, for instance, if we were given sine or cos of n times x, then the period from a previous video, the period is given by 2 pi on n. So if n is 2, then 2 pi on 2 will give us pi. So we have a period here clearly of pi. So what the factor of 2 has done here, it's doubled the number of solutions. We've now got 4 solutions, 2, 3, 4, when solving over the same 2 pi interval. But what the factor of 2 has done here has dilated the sine x graph by a factor of a half in the x direction. It's shortened it. It's shortened so that its period is now half of what it was before. As a result, it now has 2 cycles within the same 2 pi, okay, resulting in 4 solutions. So the factor of 2 has doubled the number of solutions. And if we had sine 3x there, you'd triple the number of solutions. And if we had sine 4x, you would quadruple the number of solutions, and so on. Okay, so bear that in mind when we solve equations, trigonometric equations. Let's go on to have a look at 2 examples in a little bit of detail. Okay, so we're going to start here. Here's example 1. Okay, we're going to solve square root 2 times sine in brackets 3 parentheses x minus pi on 4 in parentheses plus 1 is 0. Okay, and we want to solve that for the interval x belongs to 0 to 2 pi, including the endpoints. Okay, well, let's just transpose this. We'll take the plus 1 on the other side to make it minus 1, and then we'll divide through by square root of 2. So we're left with the sine of the argument stated before, 3 parentheses x minus pi on 4 close parentheses, is equal to minus 1 on root 2. Okay, just for future reference, we'll just label the argument here. That's this algebraic expression in here. We'll just give that letter theta. That'll simplify things, and you'll see why shortly. Okay, now let's note something. Let's just come back to this interval. So x lies between 0 and 2 pi, including the endpoints. If I were now, say, to start to transform this interval, because you notice in the argument here, I've got x minus pi on 4, and then I times a whole lot, the result of that, by 3. So let's just start inside the parentheses, and let's subtract pi on 4. So we do that from all 3 terms in here within this inequality. And we have minus pi on 4, 0 minus pi on 4 is minus pi on 4. X minus pi on 4 is x minus pi on 4. 2 pi minus pi on 4 will give us 7 pi on 4. 2 pi is the same as 8 pi on 4. Minus pi on 4 gives us 7 pi on 4. Okay, next thing now, let's multiply through by plus 3. Okay, so we have minus 3 pi on 4 is equal to less than, here's our original argument again, is equal to less than 21 pi on 4. What we're doing is we're solving this whole argument over the interval minus 3 pi on 4 to 21 pi on 4. Okay, all right. So there's our transformed interval, and our solutions will range in this area here, in this region, for this theta object. Okay, now, so essentially what we want to now do is solve sine theta is minus 1 on root 2. And we want to solve it for theta between minus 3 pi on 4 and 21 pi on 4. Okay, now sine is negative in the 3rd and 4th quadrants. And just to remind you of that good old rule, here's our quadrants. Okay, all are positive. Sine cos and tan are all positive in the first quadrant. Sine is positive in the second quadrant. Cos is positive in the third quadrant. Tan is positive in the third quadrant. Cos, is positive in the fourth quadrant. So all stations 2 central, if you want to remember it that way. Okay, so we're solving for sine being negative, and we know that sine is negative in the third and the fourth quadrants. Okay, so sine is negative in the third and fourth quadrant. So sine theta. Now what we do is we go back and we find the related first quadrant angle. So we set sine theta equal to plus 1 on root 2 to find out its value in the first quadrant. Okay, in the first quadrant, theta inverse sine 1 on root 2 is pi on 4 in the first quadrant. In the third quadrant now, remember in the second quadrant the solution is then pi minus theta. In the third quadrant it's pi plus theta, and in the fourth quadrant it's 2 pi minus theta. Okay, so in the third quadrant theta is pi plus pi on 4. The solution in the third quadrant, is 5 pi on 4. In the fourth quadrant the solution theta is 2 pi minus pi on 4, which gives us 7 pi on 4. Okay, so there's our first two solutions, 5 pi on 4, 7 pi on 4. Okay, how does that relate to this interval up here? I mean, how does it relate to that? Okay, well, first, one thing we need to notice is that 5 pi on 4, okay, is actually equal to, remember 5 pi on 4 is in the third quadrant, it's actually equal to minus 3 pi on 4. Now, minus 3 pi on 4 actually agrees with the endpoint here of our transformed interval. 7 pi on 4 is equal to minus pi on 4. Okay, so minus pi on 4, which clearly lies in this range. So there's our first two solutions. All right, there's our first two solutions. Minus 3 pi on 4, which lies in the third quadrant, comes round in the clockwise direction. And then 7 pi on 4 is minus pi on 4. So there's our first two solutions. They're at the left-hand end of this interval. One is the end of the interval itself. That's this one. And the other one is the next one along, the next closest one. Okay, so what we do is scroll the page down. Why am I having trouble scrolling this page down? That's better. Oops. Okay, my apologies there. I'm not sure what happened there. Okay, so now what we have, write out the first two solutions. Theta equals minus 3 pi on 4, minus pi on 4. And then what we do is we add on 2 pi. Remember we expected 6 solutions. Okay, so we're going to have, and we'll have a little bit over the end as well. I'll talk about that shortly. So we start with our first two solutions. Here we are. My pen is playing up. Start with the first two solutions. Then one more revolution. So we add on 2 pi to each of those. Okay. And then one more revolution. Remember, we expect 3 revolutions. So we add on 4 pi. And then we just put in one more just to check to see if that's going to be in the end interval. And I'll talk about why that is later. Okay, so working it out, we've got minus 3 pi on 4, minus pi on 4, 5 pi on 4, 7 pi on 4. Working all this out, 13 pi on 4, 15 pi on 4, 21 pi on 4. Now, 21 pi on 4 was the upper end of our interval, so it was correct to include that. Okay, originally our interval was, if I come here, originally our interval was 0 to 2 pi. Now 0 and 2 pi are the same. Okay, they're actually the same value. So there is actually one extra solution because you're really just repeating the same interval again. 0 and 2 pi are the same value. Okay, so as a result, we end up with one extra solution. All right, next thing. Theta is equal to 3 times parentheses x minus pi on 4. Okay, so it's equal to all of that we just found. So let's divide through by 3 because we want to solve for x. Remember, the original problem was in terms of x, so we want to solve for x. X minus pi on 4. Okay, so what we're going to do is divide through by 3, so we get minus 3 pi on 12. These all become 12s underneath. Previous line, they were all 4s. Okay, So we just multiply by 3. Next thing we need to do is we need to add pi on 4 to both sides. Now if I add pi on 4 here, this will bring me to 0. Pi on 4 here, 2 pi on 12, 8 pi on 12, 10 pi on 12, 13, 16 pi on 12, 18 pi on 12, 24 pi on 12. Now if we simplify those, we're left with x equals 0, pi on 6, 2 pi on 3, 5 pi on 6, 4 pi on 3, 3 pi on 2, and 2 pi. But notice 0 and 2 pi are the same, so it's just a repetition. Okay, we're back to the beginning again. Okay, that's why we get the extra solution. So we've actually got 2, 4, 6, that extra one there. Okay, now just as a visual representative, remember 5 pi on 4 going around clockwise is this angle, but that's the same as minus 3 pi on 4. All right, so that's how we did that earlier. Let's have a look at another solution now. This time we'll go to the tangent function, and a tangent function is has a period of pi, and so every pi you have a new branch. 0 to pi, one branch. Next one is pi to 2 pi, another branch, and so on, going back the other way. We'll deal with the plot of those later in another video. What we're going to do now is we're going to solve it, theta, on the interval minus pi to pi. Okay. Now this interval, the endpoints are included because square brackets. Okay. So we have minus pi to pi means we want the union of the region minus pi to 0 and union with 0 to pi. Okay, so tan theta repeats itself every pi. When we say pi, we're going around clockwise. When we say minus pi, we're going around, sorry, when we say pi, we're going around anti-clockwise. When we say minus pi, we're going around clockwise. My apologies if I said the wrong thing earlier. Okay, so now we've got here theta minus pi to pi. And what we're going to do is theta minus pi on 4. So let's subtract pi on 4 from both sides here, from all terms, sorry, within the inequality. So we have minus pi on 4, theta minus pi on 4, pi minus pi on 4. Okay, next step now was to multiply this by 3. Sorry, before I do that, let me work that. Minus 5 pi on 4, theta minus pi on 4, 3 pi on 4. Let me now multiply by 3, so we get minus 15 pi on 4, 3 times theta minus pi on 4 in parentheses, 9 pi on 4. Okay, now, next bit. We're going to let alpha equal our previous argument, 3 parentheses theta minus pi on 4. And what we notice is that tan alpha equals 1 is now the equation we want to solve. Okay, and if we remember that now tan alpha is positive in the first and third quadrants, because if you remember that basic rule, all are positive in the first, sine in the second, tan in the third, cosine in the fourth. So tan is positive in the first and third quadrant. So here basic angle is theta, here it's pi plus theta. So we find the basic angle theta, and then we can generate the solution in the third quadrant being pi plus theta. Tan alpha is positive in the first and third quadrants, and the first quadrant alpha is inverse tan of 1, which is pi on 4. All right, in the third quadrant, alpha is pi plus pi on 4. Okay, remember pi on 4 is the basic angle, and then we add pi to it for the third quadrant, so pi plus pi on 4 is 5 pi on 4. Now 5 pi on 4, if you remembered earlier, we had that just up here. 5 pi on 4 is the same as minus 3 pi on 4. All right, minus 3 pi on 4, so just be aware of that. You need to look for that at times. Now we must find all the solutions between minus 15 pi on 4 and 9 pi on 4. Okay, so here we go. Let's start here. Alpha is pi on 4. Okay, and the other solution we had was minus 3 pi on 4. Okay, and remember we're going to have 3 lots. So we're going to have first lot, second lot, third lot, and then that extra one. Okay, so we got pi on 4, minus 3 pi on 4. Then the next revolution, we've got to add a pi to both. Okay, next, and then 2 pi. Okay, and then one more, we'll add the 3 pi. So what we get is pi on 4 minus 3 pi on 4. This is 5 pi on 4 minus 7 pi on 4, 9 pi on 4, minus 11 pi on 4, minus 15 pi on 4, which agrees with what we found earlier. Here's the interval. over which we're interested in. Okay, let's put that down now. Let's remove the alpha now and replace it with our original argument, 3 times theta minus pi on 4, and transfer everything from the line just above down to here. Okay, now step 1, we're going to divide by 3, so let's just multiply the denominators by 3 again, hence the 12s underneath. Nothing in the numerator changes. Then we're going to add pi on 4 to both, all right, which gives us 4 pi on 12, 0, 8 pi on 12, minus 4 pi on 12, 12 pi on 12, minus 8 pi on 12, minus 12 pi on 12. Now, you can do those calculations for yourself just to verify that, but I don't want to distract you by doing that. I just want to keep the focus on the activity here, on the process. So simplifying, pi on 3, 0, 2 pi on 3, minus pi on 3, pi, minus 2 pi on 3, and minus pi. Okay, so there are our solutions for tan 3 theta minus pi on 4 equals to 1. All right, that's it then. Done.